sometimes even the most powerful computer in the world can be defeated by what looks like a simple problem. If I have a volunteer, I can show you an example. Who'd like to come on down? Let's have you. Okay, come on. Let's just turn around there. What's your name?
Reese.
Reese. Okay, Reese. What I have here is a very simple looking puzzle for you to solve. There are 4 pieces, and all I want you to do is take these pieces and, that's it, you get hold of it, and lock them together to make a 2x2 pattern there, okay? Now this looks like a fairly simple puzzle, and you'd think that a computer would be very good at this, because after all, the computer just has to try lots and lots of different possibilities until it finds the answer. The problem comes if we make the puzzle a little bit bigger. Here I have an example that's 3x3, so this has 9 pieces. Now if I've got a computer that can look at 1,000,000 different positions a second, then it would only take a blink of an eye to do that puzzle. But if I jumbled up these pieces, it would take over a day to solve this. Okay, how are we getting on? Shall I just give you a little bit of a clue here? There we go. Okay, good. Can you fit that one in? Okay, that's looking promising. Excellent. Okay, well done. Thank you very much. So if my computer doing 1,000,000 moves a second takes a day to solve that puzzle, what about this puzzle? This is 5x5, so this has got 25 pieces in it. So if it takes a day to solve that one, how long do you think it would take to solve this one? Any idea? 4 days? Any other ideas? A year. Somebody thinks it would take a year. This is how long it would take to solve this puzzle if my computer tries 1,000,000 moves a second. It would be 500 trillion years to solve this puzzle. That's a long time. The universe is a mere 14 billion years old. Now, of course, we could speed it up a little bit because the computer doesn't need to look at every possibility, but it would still take an astronomically long time to solve this puzzle. You might think, well, instead of trying lots of different possibilities, is there a really clever method that would allow a computer to solve a puzzle like this in, let's say, a few weeks? Well, surprisingly, no one knows. It's one of the big open challenges of computer science. And it's not just puzzles like this which are hard to solve. There are many practical problems, such as working out the perfect school timetable, or in my field, working out how to lay out the electrical components on a circuit board that are so complex we simply have no hope of ever finding the exact solution. But physicists and computer scientists are exploring a radically different kind of machine called a quantum computer, which one day might be able to solve at least some of these very difficult problems. To see how that works, I've got a demonstration here. In this box at the bottom, we have a source of microwaves. And the microwaves are being beamed up here to this metal plate. Now, this metal plate has 2 slits in it, so the microwaves are coming up through those slits. And I have here a detector of microwaves, and it's going to make a sound. And the louder the sound, the stronger the microwaves. Now, you might expect that with 2 slits, I would have 2 regions where the microwaves are strong and the sound is loud. But let's see what actually happens. Listen carefully to this. Okay, it's getting stronger and quieter. Each of these yellow bands is a region where the microwaves are strong. So instead of having just 2 regions where the microwaves are strong, we've got quite a few. This seems very strange. What's going on here is that the microwaves are coming up through those 2 slits. Because they're waves, in certain places the waves go up and down together and they add up and it's strong. But in between, the waves are going in opposite directions and they cancel out. So this tells us that the microwaves are coming through both slits at the same time. Now, if we repeat that experiment using light instead of microwaves, and we use very small slits, we see this. Each of these little dots is a particle of light called a photon. But if we wait long enough, and this whole experiment takes about half an hour to run, so we've speeded it up here, the photons build up into vertical bands or stripes, which are very much like the bands that we saw on the microwave experiment. So that means that those photons, those particles of light, must have gone through both slits at the same time. Now, this is an extremely peculiar quantum phenomenon. It's called superposition, the idea that something can be in two places at the same time. And it's not just photons that can be in two places at the same time. This is a model of a molecule called carbon-60, or a buckyball. Each of these is a carbon atom. And molecules as big as this have been put into a superposition, in which the molecule is in two different places at the same time. Thank you. But how can we make use of superposition to build a computer? Well, to find out, we have two people who are wearing, I hope, very special T-shirts. Where are they? They're hiding somewhere. Yes, do you want to come on down? Okay, if you'd like to come on down here. And what's your name?
Holly.
Holly, if you'd like to come and stand there. And your name?
Alex.
Alex. Now, Holly and Alex are wearing very, very expensive T-shirts, because these are quantum T-shirts. Now, if we just stand back a second, let's imagine that Holly here is a bit, a binary digit, in an ordinary computer. Now, the computer could first of all process the value 1, and that would take one run of the computer. Now, if you'd like to turn around, that's it, and stop there, good. The computer could then run a second time and process the value 0, so it would have to run 2 times. Okay, you can turn around and face the front now. But if you were a quantum bit in a quantum computer, then you could be in a superposition of both 0 and 1 at the same time. And using the magic of television, we can see what that might look like. So a quantum computer could process that superposition in 1 step instead of in 2 steps like a classical computer. So a quantum computer could be twice as fast as a classical conventional computer. Now, that may not sound very exciting, but let's see what happens if we add in another quantum bit. So if you'd like to come and stand there. And so when you're both facing forward, you're both in the 1 state. If you turn around, both of you, that's good. Now you're both a 0. And if you turn back to the front again, there are actually here, that's good, you can turn to face the front, that's good. There are actually 4 possibilities here, 1, 1, 1, 0, 0, 1, and 0, 0. So a conventional computer would have to process each of those 4 possibilities, one after the other. It would have to run 4 times. But if you look up on the screen, we'll see what a quantum superposition would look like, and that contains all 4 possibilities. So a quantum computer could do 4 things at once. So with 2 bits, it would be 4 times as fast as a conventional computer. And if you recall from earlier, every time we add another bit, we double the number of possibilities. So if we have a quantum computer with, let's say, 300 quantum bits, it would be able to do more things at the same time than there are atoms in the universe. And that's powerful enough to solve some of those tough problems that we talked about earlier. Now, quantum computers won't solve all of those problems, and they won't be general-purpose computers. But one day, they could solve problems that simply can't be solved in any other way. Okay, back to your seats now. Thank you very much. Now, you might have noticed that you can't buy quantum computers in the shops just yet. And there's a good reason for that. The reason is that this superposition state is incredibly fragile. Even the tiniest disturbance will destroy it. At the moment, the most complex calculation that's ever been done by a quantum computer is to show that the number 15 is equal to 3 times 5. So not very impressive, but there are lots and lots of ideas for ways to build practical quantum computers. So in perhaps 30 years' time, when some of you are scientists, we might see the first large-scale quantum computers. Until then, we're faced with computational problems that are so difficult, there is simply no hope of any computer solving them. Now, that might sound like bad news, but in fact, we can use it to our advantage. Every time we send secret information over the internet, such as our name and address or credit card information, we're relying on these very hard computational problems in order to keep it secure. To find out why, join me for tomorrow's lecture when we'll be untangling some of the secrets of the web. Thank you.